Hello, everyone. Today we are going to discuss some specialized software for uh, cheminformatics and the software we are going to use in our upcoming workshops. But before that, I must say several words about the PyTorch library. This is an open source framework for machine learning, and it's most frequently used for training artificial neural networks in the research community. So it is tuned to work with tensor objects efficiently, just like the NumPy library is centered around arrays, and it allows efficient computations on GPUs or simply video cards. This is because GPUs, because of the parallel architecture of modern GPUs that allows us perform computations with tensors efficiently. And we are not going to use the PyTorch library in our workshops due to the design of the course. However, I would like to suggest you the courses by the Intellect Foundation and several. One of the courses is on training neural networks in research. So this is a course for MSU students of several stages. For master students and for PhD students, I suggest you enrolling in this course. These guys are true professionals, and if you are going to use, if you want to use neural networks in your research, so I suggest you enroll in. Just in case you haven't managed to enroll in this course, you can try this step-by-step guide that will help you to get familiar with the PyTorch library. And so it's a tutorial that will help you in case you've missed this course. Speaking about the PyTorch library, it allows us to make several important things, and it includes the Avogadro package for automated differentiation. So we will briefly discuss how neural networks are structured and why do we need differentiation when training neural networks. It includes loss functions like root mean square deviation, and so a little bit about this later as well. So it includes the module class for neural network models, and it includes activation functions as well. So it's simply, it can be installed simply by using Anaconda. And so good luck if you are going to use neural networks. I suggest you doing tutorial and enroll in the course I've told you about. And now let's proceed to our first program that we are going to need in our workshops, and we are going to discuss today. So now I'm speaking about the Avogadro molecular editor that allows you to do several important things. First of all, it allows us building 3D models of molecules, like drawing molecules, and perform geometry optimizations with molecular mechanics methods. We are going to discuss what molecular mechanics is today, a little bit later. Also, it allows us visualizing molecular models in high quality. So if you are interested in producing high quality figures for your publications, you may want to use the POVRE program that I'm going to mention a little bit later. And also, last but not least, Avogadro molecular editor allows us saving and converting 3D models of molecules in several file formats that we also going to discuss in the upcoming lectures. The Avogadro molecular editor has an official site that I suggest you visiting. So it's avogadro.cc, and so you can download the editor. It's available from the sourceforge.net, and well, I should also say that it's a cross-platform program, so it's available for Windows and Mac platforms. You can easily download the program and install it. Also, if you are using a Linux operating system, one of the distributions, you can install the editor from your distributions repository. However, speaking about version control, I strongly suggest you install the version 1.2.0. So I use this version for several reasons. I find it the most convenient. And if you are going to install the editor via the repository of your of Linux, so try to install this particular version. And this also is applicable to downloading and installing the version for Windows and Mac. And there is a original publication on the editor. So it's from 2012. However, the program is actively supported by the community. It's a free program, so community often releases some updates, and in the original publications, they discuss the program structure, its features, and so what libraries it uses for its for providing its features, So I should also say that there is an online manual, so you can on the original site you can go by this link. So the program is well documented, and I suggest you surfing through the manual. We are going to discuss basic features I've told you about in several minutes. However, I suggest you visiting the online manual as well. In the Avogadro editor, we can use molecular mechanics methods that in which and in the constant of molecular mechanics methods, we need to discuss force fields that are combinations of functions called potentials and parameters for these functions. So every force field has parameters, has force constants and equilibrium values for particular atomic types. For example, you will have different equilibrium bond distances for alkanes or alkenes. And so you will also have different force constants. Also, in many organic molecules, we have dihedral angles. So these are angles between that describe rotation around molecular bonds, like this, for example. So this every dihedral angle is described by 4 points. Let me show you in more detail. So here we have a butane molecule, and to define a dihedral angle, so we need 4 points. Let it be these 4. So we optimized the molecular structure, and now let's define a dihedral angle. So basically, the angle that I show you here is the dihedral angle that is defined by these 4 points. So if we want to describe the rotation around this bond, we need to have we may use dihedral angle that will differ along with the rotation of this metal group, like this. So molecular mechanics force fields also include terms for dihedral angles. They also can include some additional terms like improper angles, and all these terms are related to covalent interactions between atoms. So they are related to covalent interactions. And in particular to intermolecular, they are related to intermolecular interactions as opposed to intermolecular interactions. So if we have, for example, two molecules like this, they can be in close contact. Like I'm showing here. So this an interaction between this molecule and that this one would be an intermolecular interaction. So for intermolecular interactions, we should also have two terms. First of all, we have the so-called, here we have the so-called Lennard-Jones potential that describes repulsion between two molecules that is related to the repulsion between atomic electron shells. And also we have an attractive term that is related to dispersion attraction. We will discuss intermolecular interactions and all this a little bit later in our course. And for now, I should also mention that as long as many molecules exhibit partial charges, so in organic chemistry, you can have some delta minuses and delta pluses on some atoms, so you can have an uncompensated charge in several in some molecular parts, and molecules can be attracted to each other due to the electrostatic interactions. So many modern molecular force fields include Coulomb terms like this one that describe electrostatic attraction. And I've shown you a couple of examples. We also can draw a more difficult molecule. Let's draw a molecule that exhibits aromatic cycles, for example. First of all, let's draw a double bond. Next, we draw a cycle, and in the end, we have a benzene molecule. So we can optimize its structure and get benzene with equilibrium bond distances like this. Again, bond distances can be a little bit over or underestimated due to inaccuracies of the used force fields. However, this is inevitable due to simplicity of molecular force fields. So, however, this, because of the same simplicity, molecular mechanics methods are a great tool for initial optimization of molecular structures. So by using Avogadro, you can draw simple molecules that we are going to need, and you can pre-optimize their structure to make it meaningful. Speaking about molecular structure visualization, I should also mention the Jmol program. Jmol is an open source molecular visualizer, so it can be easily downloaded from the SourceForge. And you can easily find it. Just follow the link I provide you. It's easily installed. It's written in Java, and it's ported on many operating systems. You can use it on Windows, Mac, as well as on Linux. So you can follow the link to download the latest version. And we are going to discuss this editor as well. It's an editor that is mostly for visualizations of molecular models. For example, we can visualize the structure of the so-called aspirin molecule. So, and we will use it a little bit later. Now let's discuss a feature of the Avogadro editor that is quite useful for making high quality figures and high quality molecular models for publications. Let's complexify the benzene molecule we have drawn. So let it be this French methylated benzene. We can change the background color. So let's switch it to white. And now we can use the Foveray editor, Foveray program to render a high quality image. So to do so, we need to provide a path to the Foveray program I have here. So in my case, I suggested options are the following. Here I have options for performing ray tracing. So let's save the molecule as test aromatic in a format, in the XYZ format we are going to discuss later. So we save the molecule. And we can render it. So here we have a PNG file that contains the visualization. So it should be noted, for example, that here we have shadows and reflections. By providing different complex molecules, we can render high quality visualizations of molecular structure. So again, let's render. And we have a model of the so-called aspirin molecule. Again, the visualizations exhibits shadows, reflections, and high DPI quality. So when you are using POV for rendering images, figures in Avogadro, you need to provide a path to the executable. POV can easily be found. I can send you a link. So you can easily Google it and install on your computer. So as I've said, the Avogadro editor relies on Open Babel that we need to discuss. So Open Babel is an open source chemistry toolbox, and I would also say the open source chemistry toolbox that is very popular. The original publication is from 2011, and you can find a link. And also I provide you one. It allows us to perform several tasks, including molecular mechanics optimizations that I've shown you in a graphical way. It allows us to convert different file formats that we are going to discuss, and compute descriptors and fingerprints that we are going to discuss as well. I strongly suggest you to install the program on your computer, and it can be installed in several ways. First of all, it can be installed via Anaconda. So it's provided from the CondaForge package, and it can be installed by using this command from your command prompt that in which you have loaded your Conda environment. So, moreover, it can be easily installed on Windows computers. There is a site I suggest you visiting. So it includes info on the program, as long as and the official user guide. You can download it, and so there are distributions for the main operating systems for Windows users. You can also install a graphical version of OpenBabel, and I suggest for beginners, I suggest installing OpenBabel in two ways. First of all, I suggest you installing it with Anaconda from the CondaForge package, and also I suggest you installing it. Suggest you installing the GUI graphical version, so you can get familiar with the program. So just follow the link, and it goes to the GitHub. You can download it. Download the installer. We are going to use OpenBabel in several our projects, and it can be used in two ways. First of all, I should mention that that OpenBabel is written it's not written in Python. So to simplify using it from Python, there is Babel that provides convenience functions and classes that allow us easily execute OpenBabel tools from a Jupyter notebook or from any other Python program. So we are going to discuss Babel a little bit later. And for now, let me show you the main features of OpenBabel. The main feature of OpenBabel, most often it is used to convert different file formats that represent molecular structure in 2D or 3D. For example, we can use this command to perform the following. And before that, I'm going to show you the file that is the input for the OpenBabel program here. So we to use OpenBabel from Anaconda, from an Anaconda environment, we need to run this command, obabel. And pay attention that here I have loaded an environment called demo2 that I'm going to use in our for our demonstrations. So here I have a line. I have I specify the input in the SMI format. It stands for smiles. Smiles is a format for description of molecular structure in the form of in strings that encode molecular graphs. We will discuss this a little bit later, and here we have 4 Cs. So let's see what these 4 Cs stand for. Next, we are going to have an output. It will be in the Jmol format, and we are going to generate a 3D geometry. So the molecule is converted successfully, and let's see what we've got here. So basically we have butane. Those 4 Cs I've shown you are simply carbon atoms that we have here. So to convert different files that encode molecular structures, you should use the obabel command, and you should consult. You can have you can find the guide on the internet by following several links. So an online guide can be found on this page. So You can have it here. And there are thousands of features. However, several features are basic. For example, so as I've said, you can convert and manipulate chemical files. And convert them in this way. Another two programs we are going to need, another two libraries we are going to need are RDKit and Mordred. RDKit is an open source toolkit for Cheminformatics that is widely used. It allows us to perform several operations, including calculations of descriptors, for example, or else. It's extensively documented. So I suggest you following this link. It can be simply installed in Anaconda, and I suggest you doing that later. Again, it's installed from the Anaconda Forge channel, so you must specify the channel to properly install it. And there are several publications related to RDKit that we are going to discuss. So, another library that you are going to need is Mordred. It allows us to calculate molecular descriptors. Briefly, molecular descriptors encode molecular structure in such a way that molecular structure can be processed by computer, by a machine learning algorithm, and we can search for correlations between molecular structure and and molecular properties. Of course, we can use some molecular properties as some kind as descriptors, as features in machine learning models, and we are going to discuss that later as well. For now, I suggest you install Mordred. It can be a little bit tricky because, as I've told you, you should, when using Anaconda, you should manage your environment, and I've told you that many Anaconda packages are from the main channel are incompatible with packages from the Anaconda Forge channel. So indeed, RDKit and Mordred, some prerequisites of RDKit and Mordred are incompatible with packages from the main channel. So I suggest you set up an environment and install the Mordred library with this command. So a couple of things to guide you. The Mordred library includes a great number of molecular descriptors that encode molecular structure in different ways. We are going to discuss several of them, and we also going to use this library to establish correlations between molecular structure and biological activity later. So stay tuned for the workshop. And now I'm going to mention several, I should say several words. Should mention quantum chemical modeling because we are going to use one program for quantum chemical calculations that is simple to use and will help us to get into to understand how will help us to understand how molecular structure can be analyzed and later correlated with molecular properties. I cannot give you all the information on quantum chemistry because many courses on quantum chemistry are several semester courses and include practice and theory. We are going to use a program I've mentioned earlier, the XTB program, in a black box manner. And for now, I suggest you two books that can be introduce you in the topic. So for those of you who want to easy introduction and who also are beginners in computational chemistry, I suggest this book that is simple and can be found over in the internet. So it gives a short introduction in the field of computational chemistry. And for those of you who want to get a detailed picture, I suggest this book by Frank Jensen that describes most of quantum chemical methods that are used today. The first or second editions may be a little bit outdated. However, the basics is the same. So this is a strongly suggested reading for those of you who are interested in molecular modeling. And when we mention quantum chemistry, when we speak about quantum chemistry, there are several fundamental pros and cons of quantum chemical methods as a research tool. Basically, most quantum chemical calculations, at least most conventional quantum chemical calculations, are based on the stationary Schrödinger equation that may seem basically simple. However, well, in practice, it's a really difficult equation to solve, and this book gives many approaches to solving it in several hundreds of pages. So first of all, the Schrödinger equation includes the wave function. The wave function describes a molecular system, and by knowing it, you can calculate any physical property of this system. By using quantum chemistry and by using the Schrödinger equation, it is possible to model any molecular system or any chemical system from the first principles. So you just know the equation and you can try to solve it. However, you cannot solve it analytically. So there are some caveats with this. And again, by using the Schrödinger equation, you can infer an optimal structure of a given molecular system, and without knowing without only a guess of this structure. However, all these pros are countered by cons, so it's highly complex. Finding the wave function is a complex process. It's quite difficult to solve the Schrödinger equation, and in practice, you should have a very good guess of the molecular structure or the structure of a given molecular system. We are going to, in the course, we are going to discuss mostly machine learning approaches. However, we are going to discuss the so-called semi-empirical methods as well. And in particular, one semi-empirical method that is called GFN XTB2. Before that, I'm going to leave you several slides for home reading to that describe why solving a stationary Schrödinger equation is a complex task. Basically, when you have a system of many particles, let it be several nuclei and several electrons, you cannot separate variables and you cannot solve this equation. You can, some of you can also ask why we cannot only cancel, why don't the wave function simply cancel? Why doesn't it simply cancel out? It's because here we have the Hamilton operator that has quite complex structure, so you cannot perform this cannot simplify the equation this way. So, and this is the energy, is the total energy of the molecular system. For a simple system, like a hydrogen atom, you can use spherical coordinate system to separate variables, and after solving, and you can solve, by doing so, you can solve the equation analytically. After, well, as a result, you will get solutions that depend on integer numbers, and you know these numbers from school. It's NLM quantum numbers. These are within spherical the so-called spherical harmonics. So these are functions that look like these, and visualizing them, you understand that these functions are familiar to you, so they were developed much before the Schrödinger equation, and so now they are actively used in the field of quantum chemistry. So these are spherical harmonics that are simply functions that include integer numbers. Next, we have these exponents that depend on the charge of the nucleus. So these are the so-called Slater type exponents that have r, the distance from the nucleus, here. And combining these spherical harmonics and Slater type exponents, we get atomic orbitals of hydrogen-like species, like hydrogen atom, helium ion, monocation, and lithium dication, etc. So all these systems exhibit only one electron, and these solutions, these functions that are solutions of the Schrödinger differential equations, are the so-called atomic orbitals. These atomic orbitals, after some fine-tuning, can be used for quantum chemical calculations, and some of you are familiar with the molecular orbital theory and the methods of linear combination of atomic orbitals. In this method, molecular orbitals that are orbitals, basically are orbitals of a molecular system, are combined, are represented by a linear combination of atomic orbitals, so that we have a linear sum. You can also, I suggest you also Google the method for those of you who haven't heard about it. So these molecular orbitals can be combined to have wave function of a molecular system. And to simply solve this equation, we should also get some approximations to the Hamiltonian operator that describes energy of a given molecular system. To get there are many approximations to the Schrödinger equation, and the approximation we are going to discuss is the GFM2XTB method. There is an original publication on the method, so you can have it here. It's free to download, and basically the method describes molecular energy as a sum of several interactions that are described in the article. All these terms are described in the article. As long as we are going to use the method in a black box manner, I'm going to skip the discussion, but you are encouraged to get familiar with the original publication. And this method is implemented in the XTB program. On the last lesson, or some of you had trouble with the XTB that cannot be installed as a conda package yet. So now it can be installed as a conda package, but Windows users can install it by following this link and download the installer for Windows. So I suggest you doing that. And as I've told you, there are some distributions for Windows, so there are some indeed. For conda users, for Linux and Mac users, I suggest installing it from Anaconda with this command. So after installing it, you can perform several simple computations with this method. So let's do some simple computations like geometry optimization and or else. Here I have a butene molecule that I've drawn before the lesson. So it has some molecular structure with elongated, the structure represents elongated bonds. So let's perform geometry optimization to get a better representation of molecular geometry. So please remember to activate the needed conda environment, and by performing this command, we have by inputting this command, we perform geometry optimization that proceeds very fast due to just because this is a simple method and we have a small molecule. So now we can have a much better representation of interatomic distances, and we have an optimized structure. Next, we can also perform vibrational frequency analysis with this program. Again, and before entering the command, I should also mention what vibrational frequency analysis is. For those of you who want to read about the XTB program, I suggest the original, the official guide. It includes all topics like geometry optimization and calculation of vibrational frequencies and many others. So, speaking about vibrational frequencies, this can be simply imagined like vibrations of atoms of different kinds. There are several known types of molecular vibrations, and you may ask, do molecules really vibrate? And in fact, yes, they do. They do that even at ambient conditions very actively, and you can force molecules to vibrate by using infrared light. So, for example, you can use infrared spectroscopy or other types of vibrational spectroscopy to force molecules to vibrate. This usually leads to heating of molecules because in the vibration, kinetic energy is stored in the vibrational molecular motion. So I suggest you this link to get into that topic. And there is a simple explanation for molecular vibrations and for vibration physical. There is a simple physical mechanistic explanation for vibrational spectroscopy. So molecules can absorb quanta of infrared light, and by doing so, by absorbing infrared light of particular frequencies, some bones or angles can start to vibrate. vibrational frequency is related to several parameters like force constant or mass. And force constant is related to the second derivative of potential energy. So by analyzing vibrational frequencies, we basically analyze if we have a minimum of potential energy or not. So we analyze second derivatives of potential energy. Potential energy surface is a fundamental property, is a fundamental function of model molecular systems. We are also going to discuss later. For now, let me just say that checking if you have a minimum on the potential energy surface or not is important for analysis. So, and we have significant imaginary frequencies. For our purposes, there is no it's not important if we have imaginary frequencies or not. However, I need to mention that the molecular model here this molecular model is not a minimum on the potential energy surface. So we also can perform molecular dynamics simulations by using the XTB program. It is done simply with this command, and so to perform a molecular dynamic simulation, we need to have this file in the working directory. It defines parameters of the molecular dynamic simulations of the molecular dynamic simulation you are going to perform, and you can find all descriptions of all parameters in the guide. So here, like temperature and other parameters. So let's let's run a molecular dynamics simulation and see what happens. By running a simulation, when running a simulation, you see the output like this. And in the working directory, you can see this file called xtb.trj. This is the trajectory that is simulated. With the program. So I'm using the Jmol visualizer, and I can run the simulation. I can visualize the simulation. Here, for example, we see that the metal group starts to rotate around the axis that is here. And basically, we simulate molecular motion with the molecular dynamics method. There are several approaches to simulation. There are many approaches to simulation, molecular dynamics simulations. And here we use the XTB program and the GFN2 XTB method to simulate molecular motions that we can can occur in the gas phase. So if we evaporate aspirin and isolate molecules from the vapor, several molecules, we can expect that these molecules will vibrate the way we see now. Like this. Now I'm going to stop the simulation, and I'm going to show you a feature of the Jmol editor that I suggest you to use. So as Avogadro allows us to render molecular models, Jmol editor allows us to render molecular models and make molecular movies from molecular dynamics trajectories. So I provide this example script that will allow you to render all snapshots from the trajectory with Jmol. So in the working directory, that is the folder that contains the Jmol program, we have all we have all files. We have all visualizations of different frames. And now we can use several programs to make molecular movies, to make a molecular movie from these snapshots. So I use memcoder that can be installed from in Linux, and I guess it can be installed on Mac with the Homebrew. So for those of you who are interested in visualizations of molecular movies, I can provide you a more detailed description on how to make these molecular movies. So and here we go. So basically we have a molecular movie like this. We can compress it. So I provide all these commands for you to use later. For those of you interested in molecular reactivity, I suggest you compare molecular dynamics simulations with metadynamic simulations that can be done by using the XTB program, and that will be all for today. So thank you.